So in this video, what I'd like to do is think about flux at the sort of differential level. And where we're going with this is we're trying to connect we're trying to connect flux to that upside down triangle that we saw earlier when we were talking about gradient. In particular, we're going to connect flux to the idea of the divergence of a vector field. So we're going to look at a really sort of simple example. This is an example that makes mathematicians cringe, so I apologize to my colleagues, but I'm going to do it anyways. So I'm going to think about some point x comma y. Right? I'm just going to work in two dimensions for this. The sort of idea, I think you'll see, applies to a higher number of dimensions as well. And I'm going to think about some little contour that surrounds that point x comma y. Right? It has length dx in one direction and length dy in the other direction. Right? So this is sort of a differential area, dA. And you could also think about this as a contour, C that goes, it's a closed contour that goes around that point. Okay? Now for this, I'm going to think about this situation where I've got this closed contour and I've got some vector field that I'm interested in calculating the flux of that vector field through this closed contour. So I'm given some vector field f, right? Maybe it's the velocity field, maybe it's a sort of energy, sort of current, it could be any vector field, and I'd like to figure out what's the flux of the vector field through this contour f, or through this contour C. In other words, net, how much f is coming out of this little chunk. Okay. Well, conceptually, we sort of know how to write out the coordinate-free integral for that. The coordinate-free integral for that flux is going to be the closed integral around that contour C of the vector field dotted with n hat dl, right? We're working in two dimensions, so we're walking around this contour, and at each point around that contour, we're looking at how much flux is coming out of each little bit of that contour, right? And of course, I could think about that, since it's a square, I can think about that as breaking up into four parts, right? So we'll call this part 1, this part 2, this part 3, and this part 4, right? So I'm going to have the integral along line 1 of n hat dl, right, plus the integral along line 2 f dot n hat dl, etc. Right? Okay. Now, if I think about what the flux is for contour number 1, or if I think about what the unit vectors are, for contour number 1, this n hat is minus j hat, right? And for contour number 2, this n hat is plus I hat. For contour number 3, it's plus j hat. For contour number 4, it's minus I hat, right? So I could actually go ahead and think about, let's just think about this first one a little bit. I've got the integral across this line of the value of the vector field along that line. So this is going to be, this first integral is going to be approximately the value of f at the point x comma y minus delta y over 2, right? Dotted with j hat, right? And this is just an approximation to what the value will be, times that little length. And that little length, of course, is dx, right? And I could do the same thing for this next point, right? So I'll get a plus f at x plus delta x over 2 comma y, dotted with I hat, and this should be a minus here because this is a minus j hat, right? dy, right? And then I will get a plus the vector at x comma y plus delta y over 2 dot j hat dx, and then finally a minus the vector at x minus delta x over 2 y dot I hat dy. Okay? So all I'm doing is just saying how much flux is coming out of this chunk, how much flux is coming out of this chunk, how much is out of this chunk, and how much is out of this chunk. Now if I collect terms here, I've got this term, right, which looks like, if I bring this over here, this is just the y component of f, right, evaluated at the point y minus delta y, and this is the y component of f evaluated at the point y plus delta y over 2. So that looks like the y component of f, and I apologize for this notation, but the y component of f evaluated at x comma y plus delta y over 2 minus the y component of f at x comma y minus delta y over 2, right, all times dx. Right? And in fact, this should look pretty familiar. That looks like an awful lot like the definition of the derivative. In fact, that is the definition of the partial derivative with respect to y times dy. Right? So I'm going to relabel this as the partial of f with respect to y dy dx. Right? This interior thing is simply this part, and then it's times dx. Right? And I can do the same thing with this part and this part. I end up getting plus the partial of f with respect to x, and this is the partial of the y component and the partial of the x component, dy dx here, where the partial of f with respect to x times dy is, times dx is the stuff inside, and then I pick up the dy from here as well. So I can actually think about what the total flux is out of this chunk as simply the partial of the x component with respect to x plus the partial of the y component of f with respect to y, all times dx dy, right? In other words, it's some quantity that has to do with the derivative times the differential area. This quantity is a quantity that we call the divergence of the vector field, and we'll talk next in the next video about sort of how to think about that and where that comes from. But at this point, all we've done is seen that for at least a small square, you can think about the total flux coming out of it in terms of what the change in the vector field is as you move across the square. And if you think about that, that actually makes sense. If the vector field weren't changing at all across this square, you'd have just as much stuff coming in this side as going out that side, just as much stuff coming in this side as going out that side. The only way that I'm going to get a net flux into or out of this surface is if the vector field is changing, either if the x component is changing as I go from this side to this side, or if the y component is changing as I go from this side to this side. Right? Those are the conditions that are necessary in order for me to get a flux. Right? So my flux for this little chunk is simply given by this expression.